Okay, I'm going to share the screen and I will start. Good evening, everybody. Welcome to our second meeting, um, looking at the math map. This week, I want to focus on the domains part of the math map. As you know, the domains is the top of the grid. When you look at the math map grid inside the booklets, you'll notice that giant grid. The top of it talks about the domains, and you basically do one domain a year, going from 5 to 17-year-olds. And I wanted to just, kind of go through why we do this, and what domains are. So here I have a presentation, and I would hope that you may learn something through this. So as you see here, domains, the categories of numbers. So let's move on, and we will talk about these domains. So as I said, you're going to basically do domains each year. This is kind of the schedule, approximate schedule. It is actually more at the parent's discretion of when you want to do these different domains. So if you have someone who's struggling, it's probably beneficial just to go to naturals, even though it's the approximate age in the order of the domains, about 6 years old, in the foundations. But you know what? It's a good practice. It's a good, just a starting level, to look at the naturals, because you're not dealing with very, very complicated numbers. You're just looking at simple numbers that you'll be able to use and learn how to do the concepts throughout the year. So that's just some suggestion, maybe advice, if you are struggling of where you want to put your child. Again, it's depends on the parent, depends on the child, how you want to go forth with which domain you want to work. But if you want to some kind of idea of where they're going to be at, these are the approximate ages. And when you get into the challenge program, they're going to be doing these specific domains per year based on which challenge you're in. So if you're in challenge A, you're going to be doing complex in class. So if you want to just be doing a lesson like fractions or something like that, that's okay. But just understand that during class, they're going to be doing complex. If they're in challenge B, like my son is this year, he'll be doing monomials. So again, these are just basic guidelines of what's the curriculum, how they set the curriculum up. But again, it's parents' discretion and based on the child. So move on. And so first of all, this term is kind of used two different ways in the math map and in math in general. So the domain versus domain. Uh, so that we're not confused about what I'm talking about here and what you'll see in the math map. You'll notice that there is going to be some things that talk about the domain of a function. So the domain of a function, it kind of describes what the inputs to a function are, and that which makes that function work. So like if you had a function like very simply like x plus 2, what is the domain, the inputs to that function x plus 2? So say 1 plus 2 is 3, and 3 would be considered the range. So you'll see, or there's my example here, 1 over x. So now in this case, it cannot be 0 because we know that you cannot divide by 0. So in this sense, when we look at that domain, it can be any number except 0. So that's kind of the domain of a function. You'll see that throughout the workbooks, but we're not looking at that one here. We're looking at number domain, the various domains of numbers that are being classified. So this describes the type of numbers being used in the context. So What I mean is if you're doing the naturals domain, we're going to be using natural numbers in the calculations. Trust me, I think you will be seeing maybe some other higher domains within the workbooks, but you won't be like trying to calculate with those. You won't be calculating with complex numbers or anything like that. You might see them and maybe have to trace them or something like that. But and there's even a week that's devoted to complex. So you'll see complex in the workbooks, but what you'll really be focusing on are the natural numbers in that case. So what is the category of numbers? What's the set of numbers that we are going to be using? And that's what we're talking about here. So you could be saying the real domain or the natural domain. Um, so that's what we're dealing with. So this is the one that we're going to be looking at tonight through this presentation. So as I say here, each year there will be a gradual increase in the types of numbers used in their calculations. So maybe if you're doing naturals, you're just going to be dealing with 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 99. But if you're say now you're into say fractions, you'll also be using 1/2, 3/4, 5 1/2, whatever be using fractions as well, plus the natural numbers because they just keep building on each other. So the domains will just be the subset of numbers they'll be using and focusing on that year. So let's basically, I want to take a walk. Take a walk. We're going on a map. We need our map. We're going on a journey. We need our map. We're going to walk through the domains in order to more understand what is the subset of those numbers that we're going to be dealing with per year. So let's start with digits. That's the again the approximate age 5. That's where supposedly they're going to start. So what are digits? So um, so these digits is basically the symbols that we use to create numbers. So we use these things that we know that we use these numbers that we use to create to be able to create those numbers. So they're the actual like kind of like the symbols, the drawings in a way. So like the drawing of a circle, which we call as a 0, drawing of maybe a line is a 1. So that's what I'm talking about. We're looking at these digits that create numbers. So I think most people are going to be already have kind of started with digits even before coming to math to doing education, going to classical conversations or wherever you're at. You're gonna already have taught them like the numbers 1 to 10. We pride ourselves on helping them, and we really are so happy when they learn how to count from 1 to 10, and it's like, oh great, you did. So these are the numbers that they probably may already are familiar with, going from 1 to 10. um I think it's we have 10 digits in our 10 fingers. So with the 10 fingers, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are these numbers that we know. And it's called the decimal system. So there's other systems, and if you look at the second week of you'll see other systems like binary and um, some other versions of numbers that we could create, but we use the decimal system. So we use these numbers are based on powers of 10. Um, but we have to understand that actually digits aren't really 1 to 10. Um, or mostly 1 to 10, but really the digits are 0 through 9. So because the number 10 is simply a combination of two of the digits. There's a 0 and a 1, but really 1 then 0 to make the number 10. And that has to do with place values. Again, that's the second week that you will be learning place values. But so these are the symbols that we use: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the ones that we combine. And you use it in the decimal system. You put in the fractions, you put in the decimal numbers, you put in uh, you know, Google, any big number, it's just a combination of all these symbols that we use, and these are the digits that we'll be using. So when they're say 5 years old, they're just learning these numbers, these simple single digit numbers, in order to do their math studies. These are the 10 symbols that create all the numbers we use in the decimal system. Um, so like just as I said, a combination of two numbers, 1 and 0, make 10. So that's probably pretty simple, pretty straightforward. So when they're at 5 years old, they're just learning how these numbers are, what these numbers are, how to draw them, how to trace them, how to um, perhaps use them to maybe add and subtract very simple equations. Um, but then we're going to move into the actual like the numbers. So those are the symbols that create the numbers. So now we're going to actually get into the actual numbers that we're going to be using. So the next year, say age 6, we're going to be using something called the natural numbers. Now, this can be a little bit confusing because there's natural numbers and there's whole numbers. We're just going to focus on natural numbers because in the math map, they basically use um, uh, they call whole numbers natural numbers. So really the difference between the two is where do they have zero or not. So natural numbers are basically counting numbers. They're the ones you count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so forth, all the way to 100, to 200, whatever. So those are, you just count with them. They're just whole numbers that you count with. Um, However, whole numbers, I think that they actually add the number 0 into it. So the math map just includes 0 in the natural numbers. So there's not these two things we have to worry about. We're just going to use natural numbers. So um, we're going to just use that as, so don't worry about whole numbers. We're just going to use counting numbers plus 0. That's your natural numbers. And I think they only use really up to 99. They're not going to go into triple digits and so forth. We're just going to use this subset of numbers in order to do our calculation. So basically natural numbers describe how many things we have. So I have one hippo. I have, 52 cards in this deck. So it just tells us how many things we have. We don't have, and we don't have a half a thing. We don't have any kind of fractionals. We don't have any of that. We just have um, stuff. We just have some stuff. And so here, as I said, some curriculums don't use 0, but some do. We're using 0 as part of the natural numbers. Um, And so we have to understand that we're not using negative numbers here. This is not, or fractions or decimals. We're not looking at that. We're keeping it very simple, just the numbers that we use to count with from 0 up to about 99. So um, at the bottom here, I put what they call the real number line, and I'm going to just add to it throughout the presentation. So as you see, we have this number line that goes from whatever infinity, negative infinity, even though we don't get to it yet. Really, it's going at this point we're going from 0 to positive infinity. Really, so that's but really we'll learn it goes to negative infinity. So I put some numbers on here. These are some natural numbers: 1, 2, 3, 4. Oh, and 0. So here we are. So that's basically what a natural number is. And so they're going to use these very simple numbers to do, again, all the different weeks and do the calculations about as they use these numbers. Okay, but now we have the next domain, which is integers. And I'm also including the universal letter symbol. Um, I didn't say anything about it last. So the naturals, they use that N. So we have the Z. Don't know which language it comes from, but they use Z. They can't use I because that's um, I'm not sure. So I think it's coming from a different language. Not everything's not in English. So Z is for the integers. Um, so this is the introduction of negative numbers. So um, basically, it's the whole number counterparts to the natural numbers. So we're including um, a -1, -2, and those type of things. So, um, at the time, we come across these negative numbers. It was kind of a foreign concept because people back then, they didn't have negative stuff. They didn't understand negative stuff. They only understood actually, the number 0 also came later because no one really had the idea of what is having nothing, having 0 of something. Because usually when we talk to numbers, they would, talk about what they had. They had 1, 2, 3, 4, whatever, how many things they had. But, um, so having 0 stuff was kind of hard. Having negative numbers was kind of complicated. Nowadays, we understand negative numbers because 'cause we're kind of immersed in, negative numbers, so we understand it in our finances or doing math in general or whatever it is, so we understand negative numbers, in some sense, I figure, but at first, it was kind of a people wouldn't understand what negative numbers were. So, like, how can you have less than 0 of something? How can you even have 0 of something? So, it's, however, using negative numbers began to allow mathematicians to solve equations that were like this, like 5 plus b equals 2. What can b be except some sort of negative number in order so a negative number that would be able to solve such an equation. Without doing that, they would just pretty much leave it like that at 5 plus b equals 2. They wouldn't be able to do go farther. There would be no solution in a sense. There you can't do that. But with the introduction of negative numbers, now we can. We can solve such an equation by calling it -3 in this example. So I'm going to add the negative numbers to our real number line. So now we're not only going 0 to infinity, but now we're going 0 backwards to negative infinity. So we're getting all these whole number integers that we can play around with in our math map. So we can begin to use we can begin to look at equations like I have there. We can look at and try to add two negative numbers or whatever. So now the kids at age 7 are now dabbling in these negative numbers. Okay, so the next 3 years, they have the kids going through decimals and fractions and rationals. So we're basically the idea of rationals has to do with what's in between the numbers. So now if you have we can divide integers. If you have, say, 2 divided by 2, you get a 1. So that's easy. Oh, if we have the number 2, we have the number 1. But what about if you divided 1 by 2? How can you take something whole and divide it up? So again, here's another um, idea that might be a little bit strange, but it began to take shape, and we start to see what we call rational numbers. It's dividing. When we divide the integers, we can find more numbers in between the integers. So not only does it go in both directions infinitely, but inside between like the number 1 and 2, we can find an infinite number of fractions. We can divide that thing out infinitely. So there's so many more numbers we can find now in between the two numbers. So as we divide the integers, we find more numbers in between. And so basically, there's rationals, and the math map doesn't really have a whole year on air rationals. But rationals is basically what it means. There's a ratio. See the word ratio here in the word rational. It's a ratio between two integers. So that's what makes it rational. So that means you can divide like the number like the half, 1 divided by 2, those are 2 separate integers, and it's that ratio, which if we look at in a decimal way, it's 0.5. We do the division, it becomes 0.5. And if or we leave it as the fraction, it's a half. So it's a ratio between two integers, where it's different when it comes to the irrational numbers, which cannot be a ratio between two integers. There are specific ones that we'll kind of look at. It can be expressed as decimals. So one year you're going to learn about decimals and how to add and subtract and multiply and all that stuff with decimal numbers. And it can be expressed as fractions as well. So that's another year talking about those fractions. Um, and so we just calculate between, or I mean, convert between the two through division. So if you divide 1/2, you put 2 into 1, it becomes 0.5. And so you can, or if you have 5/10, like 0.5, that's the same as 5/10. And when you simplify that fraction, it becomes a half again. So you can kind of convert between the two with through division and in that way. Um, so the real line is infinite in both directions, but also in between the integers. And let me just add these, um, a few of these rational numbers here on our real number line. So we're really filling in all the numbers in the real number line. So at about ages 8 through 10, we're adding more numbers that they can use to manipulate and do calculations with. So not only whole numbers, but also fractional numbers. So about age 11, we're going to get into the reals, the real domain. So this will include the irrational numbers. So irrational numbers cannot be represented as a ratio between two integers. So these are some examples that we will see, and these are ones that they'll actually memorize. And it's like pi and 11, and this this Euler's number, and also the square root of 2, which is basically diameter of a 1 by 1 square. So these are special numbers, but you can't put it, you can approximate pi with a rational number, with a, I forget what the, if it's 13/6 or some, there's some fraction you can approximate it, but you cannot get it perfectly with a ratio between two numbers. So it's considered an irrational number. So we're going to add these irrational numbers in with the rationals, and we'll get all the real numbers that we can use and manipulate. So here we are. Well, I added a few more. I added the square root of 2. I added where e is, and I added where pi is on the real number line. So we're still filling that in. And we basically, when we get to the reals, this is really where most people are, and where we tend to basically, we only need this in life. And we might not even need like pi and stuff. I mean, unless you really want to know the circumference of a circle or whatever. But in general, yeah, we're just using numbers for life. And so it really, we live here. We live in this real number line. When we think about numbers, when we think about doing whatever mathematical things that we do on a day-to-day basis, we're basically here. And so if we really understand reals, we're good. We're good. I think that's a good grasp of numbers. So we looked at this in depth. We looked at all the, going from negative infinity all the way to positive infinity and everything in between. We can plot out any point on this real number line. And yet we're not at our destination. We took the map, we're going through it, but we haven't finished all the number sets that we can do. So why is that? So why are we not finished? Why are we not at our destination? So before we really get into the complex domain, which is the final number domain, I want to take a look at this idea of closure. So when we look at to understand what closure is, It is to ask the question, what domains are closed under certain operations? So what does that mean? Um, so as an example, so say we're in the natural numbers. So remember that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 99, whatever. So say we're there. Okay. And we want to add the numbers, two of the natural numbers. We'll take the number 4 and 6. These two numbers are natural numbers, and we can add them up and we get a resulting of 10. 10 is also a natural number. And if we add two more, like 0 and 0, we get 0. Again, all natural numbers. 9 plus 1, 10. Again, natural numbers. So if we do that for addition, we will find that we can always get the result within the same domain. It will not, you don't need any more numbers. You don't need a negative number to get a result from an addition of any natural numbers. So that means that the natural number domain, those inputs will always result in a natural number, and so n is closed under addition. So we're good with addition. And we can do the same way we could do it with multiplication, and we get the same result. It's closed under multiplication. But what about subtraction? So when we do a subtraction, we can subtract. Okay, 6 minus 4. Well, that's 2. Oh, looks like we're good. It works. It's the same idea. But what if we flip those numbers and you go 4 minus 6? Now there isn't a natural number that satisfies that equation. What is, as we know, then the result would be like negative 2, negative 2, right? Negative 2. So that's not a natural number. What is that? That is an integer. So n is not closed under subtraction. And so we need, what do we need? We need new numbers. Here comes the integers. So when you add in the integers and you take it, so now the same equation works because 6 and 4 are not only natural numbers, but because natural is a subset of the integers, the integers, 6 and 4, they're also integers. It works because 2 is it works. And the same thing, if you flip them, negative 2 as the result will also work. So the integers, that domain is closed under subtraction. So we're kind of, so we got addition, we got subtraction, we got multiplication. It's all good. But then, of course, we have our next issue. We have division. And as we talked about earlier with rational numbers, we need fractions. We need rational numbers. We need, even ultimately, was with the irrationals, we need reals. So we need these new numbers in order to be able to work with the operations that we have at our disposal. So in general, we can live day to day with the real number line because we're usually just adding and subtracting numbers and maybe multiplying and dividing. These are maybe doing some exponents, I don't know, but these are the things that we do, and real numbers works for that. It's we can use most of our math in the real numbers. It's closed under almost all the operations. Of course, we can't divide by 0, so division is technically not closed for any um, domain if you include 0, but if you take that out, then it's okay. Um, so integers don't work under division, and so we end up, going through this, and I'm sorry, and then what we come to one operation. So here, one operation that will remain, that we cannot use just real numbers, and that is our good friend, the square root. So the square root is, it works for positive numbers, but not for negative. So a limitation of square root here is, as you see, if we take the powers, we square these numbers, say 2 squared, 4 squared, 6 squared, 9 squared, we can get a 4, 16, 36, 81. And if we take their counterparts and we square them, we remember that if you take two negative numbers and you multiply them together, you'll get a positive number. So you're going to get 4, 16, 36, and 81. So even if you do 2 or -2, they will result in positive number. Either one, it will always result in a positive. So if you work backwards, you're only going to be working with positive numbers. There's no way to get a negative number um, uh, in when you square a number. So um, you cannot take the square root of a negative number. So this example right here, as you see, I'm only taking square roots of positive numbers, and they will result in negative numbers. They can, it could be 2 or -2, could be 4 or -4. It works both ways, or for both results. But under the square root, you cannot take a square root of a negative number. That becomes an undefined solution in the real set. So we can't. So we need new numbers. Just like when we had natural numbers and we couldn't do 5 plus b equals 3, we needed new numbers. So we need new numbers in order to do this last operation of the square root. And so what they bearing all this, there's a lot of math details, and they were like having competitions about um how, if they could solve this equation, all this stuff. Someone used a trick of creating this because they came across a negative square root of a negative, and so they just plugged in what they call an imaginary number. They'll call it I, just to solve the equation, and everything worked out well that way. And when you do it with, you know quadratics and other higher power monomials and binomials and stuff, that's what um, they had to use this imaginary number in order to get the result. And that kind of began to bring about this complex number domain. So um, basically defining what the square root of -1 is I. They just call it I, and where it basically represents the square root of -1. And so they called it an imaginary number. That's why it's I. But it's kind of not a great name. It's not the best name. It kind of makes it sound like we make it up. Make it up on the spot. Okay, there we go. I'll imagine. So it's not a great name. There was one mathematician that kind of didn't like that name, and he really opted for something called a lateral number. A lateral number, kind of like a sidestep off the real number line. So we're usually in this one, linear space when it comes to numbers, a real number line. But with these imaginary numbers, we come off of that line, kind of a sidestep either direction. And so we'll get into that, but that's kind of the idea. So it's more of like a lateral number. So it's this imaginary number plus a real number creates what our final number domain, which is complex numbers. Well, let's see. So this is the complex number, and that's a Challenge A kids will be learning this funky number, um, something we normally don't use in day to day, because really we need to stick on that real number line. But um, it is something that mathematicians may use, engineers may use in because very complex computation is going to need this complex number. And so basically the number format here is a plus bi. And so just a note, a is a real number, and also b is a real number, but I is that imaginary number, the square root of -1. And so a by itself is what they call the real part of the complex number. And b is the imaginary part. And then not b, I'm sorry, bi, because b is actually real. It's a number like 5, but the entire thing, 5i, would be imaginary. That's the imaginary part. And you add the two together and they become a complex number. So this is our complex domain with numbers that have this format. Um, so the complex number is now closed under all operations, even including the square root of a negative number. So all numbers are in a complex number domain. They will all be there. Um, so how do we plot it? So I've been plotting this real number line the entire time. Um, we're no longer in using a real number line now, but now we're using a complex number plane. Not an airplane, of course, but like a plane is basically a concept of kind of like a giant flat piece of paper going in all directions. It's like a flat. And so the line was here, and now we're going to that was 1D, right? And now we're stretching that out this way, and it becomes a 2D, two-dimensional plane. And that's where all numbers can sit. So here's the real number line. We're going to add the imaginary axis. So that goes perpendicular. That means at a right angle or a 90-degree angle to the real number line. And that goes 1i, 2i, 3i, blah, 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 and negatives in the bottom. And so just as a note, this looks very similar to the XY plane or the Cartesian plane, but they're used very different. They're used differently. This is basically to plot out specific numbers. The XY plane has to do with an input to a function and what is its output, and that's the point at on the Cartesian plane. But here we're just looking, every point is just a number. And so that's what we're looking at here. So I'm going to plot a few different complex numbers. We're going to look at this one. So if you go to the right, you'll see it's right above the 2, but it's off the 2. It's up 2. So that's considered a complex number 2 plus 2i. If we go over here in this quadrant, we're going back on the real number line, -3, but we're going up 1i, or -3 minus I. You don't need the 1 there because it's implied that you're multiplying by 1. So -3 plus I. How about this number? We're now in between, so now we're adding some fractions here. So we got -1.5 minus 0.5i. How about this one? This one's actually on the real number line. So this is 1 plus 0i. That's the complex form. However, it's on the real number line, so the imaginary part, since it's multiplied by 0, actually can just go away, because when you multiply by 0, anything, it goes to 0. So it really equals 1, just like if it was on the real number line and we're looking at natural numbers. There's your number 1. So these are how you can plot and where all the numbers. So if it's a natural number, it's just the real part plus 0i. If it's, so if it's on the real number line, it's the imaginary part is just 0. Um, so um, so all the domains, all the number domains, so you have all the numbers that you will be working with throughout your exercises. So whatever domain you're in, those are the ones you're going to be focused on during that year. So that's all the way up to basically challenge A. So now you have all the numbers. You will actually see in your workbook an Euler diagram that shows how everything is a subset of everything else. And the main set of numbers is complex numbers. So that's all there. You could see that in your math map. I think if you look at, I think it's week 2, some of the earlier page 1 of the problems, you'll see that. So now let's look at we're going to move on to the next domains, which are more algebraic in nature, the algebraic terms under the expressions. So expressions, they use this letter A. I couldn't find the nice little bar one, so I just put the A. So this is basically ages 13 through 16. And this covers the expressions, which is the 16 year old kids, but then the three before that are the monomials, binomials, and polynomials. So an expression is basically a combination of numbers, variables, and operations without an equal sign. So the difference between an expression and an equation is that if there's an equal sign or an inequality sign, like a greater than or less than, but basically that equal makes it an equation because now you're equating two sides, two expressions on each side of of an equal sign together. So that is the difference between your expression and your equation. So now we're going to focus here on the monomials, binomials, and polynomials, which are all basically the same thing. They're just the number of terms. Like mono means one, bi means two, poly means many. So it could be three or more. Nomials, numbers, I think something like that. One set of terms. So we'll look at it a little deeper in the next slide. So these are basically good and used heavily in algebra because they're very easy to use and manipulate and work through your exercises. Um, so let's look at monomial. So basically, it has this form: ax, n, y, m. Would be more variables too. So basically, it's some a would be your like coefficient. They use the term. It's basically a number. It's a numeral coefficient, and you multiply that by some variables that are raised to some non-negative integer. So, like examples: 3x cubed y, or 15x. That just means that the y part is y to the zero. That's really all that means. And so anything to the zero power is one, so that variable would cease to be there. So that's also in that same form. And also the number five. That could be a monomial technically. So very simplified. That means all the variables are to raise to zero power. So there's only the coefficient, just the a. So that's pretty much what a monomial is. And you're just going to use this term and you're going to add and you're going to learn how to add like terms together and so forth. Binomials simply takes that monomial concept and then adds two of them and separate it by a plus or a minus. So here is an example: 3x cubed y plus 3x. So 3x cubed y is a monomial, 3x is a monomial, and you just add or subtract them. And then you have 15x minus 2. These are also examples of binomials. And then if you just keep going, now you got polynomials, which is basically many of them. So there's trinomials, so that'll be three, and it keeps going. So you'll get this. This is the more broad general term for these things. And so you see there's some trinomials right there. Um, so these expressions will be used um, into when you do like algebraic type of things and when you start getting to the higher maths. When you get to higher maths, you're not looking at numbers so much anymore. I mean, yes, you'll look at numbers, but then you do a lot of work with letters. So math becomes almost like words. They use a lot of letters because you're doing more general manipulations and finding equations that you can use rather than just specific solutions. The equations, then you can add specific numbers into the variables to create the actual solutions. But yeah, you'll use more letters in these monomials and so forth. And then finally, the last one was this transcendentals. It really has to do with these transcendental numbers, which cannot be solutions to algebraic equations. So there's a couple of famous ones that I've seen is pi and e. These, as we know, are irrational numbers, but they're also transcendental because they transcend the other numbers because you can't have them as solutions to equations. And that's where I'm going to leave that at there. Um, so here we are. So that was basically a presentation of domains and taking a walk through the domains. And if there's any questions about this, I'll can take them now. Oh, I see.
And you can do more of them. That is so cra I deleted, okay?
You deleted, okay.